to carry the torsion is called the shaft. And this could be a little bit more relevant to students majoring in mechanical engineering to petroleum, because most of such loading just happen in the shaft. And for example, civil engineering students, likely in your practice, you is less seeing the torsion of something, but kind of these things. So here in this demonstration, we look for this one is we use shaft to transmit power in terms of the torque multiplied with frequencies. Torque multiplied with rotation RPM is called the power. And this one, basically the shaft, is for the transmission of the power or energy. So here you can see, basically here is the demonstrations, and we apply the torsions to twist a shaft. And here I try to twist it. If you look at it carefully, and look at this, and this representing is a fiber on the surface of the shaft. You can see that carefully. When I say twist it, actually the fiber kind of move a little bit, right? So that is the torsions induced deformation we're going to study in this chapter. With this one, basically that is our model. We start with our generic, the fundamental model, which means we assume that is a uniform shaft. Uniform shaft is that in any cross sections, the cross-sectional area is the same. Okay, that is what we call a uniform. And for our material models we're going to work on is similar to chapter 2. We work on the uniform shaft, and with the radius, let me call it C. With the length L. This is the generic model we're going to work on. And to describe the loadings, there's a two symbols we can use. The first symbol to describe the loading, which is the torsion, just like we draw here. So if we can circulate, for example, circulate the shaft. So that means one type of loading of the torsion will be like this. I twist in this way. Okay, so I twist in this way, then the torsion is on this side is torqued in this. So that means on this side the torsion is twisted like this. And one more time, for this loading to get in balance, my hand must be twisted like this. So on this end, the torsion is go to that way. Can you see it? So that is T. This is the symbol used in most of the textbooks. Sometimes, even for myself, I have hard time to look into right direction of this. Okay, and that is my experience. So in other ways, I like to come up with different symbols. If we use our right hand rule, we use our 4 fingers to circulate the direction of the torsion. Then the thumb indicates is the direction. And then we use double arrow to indicate this is a torsion. So which means if we align our right the thumb to the double arrow directions, then the 4 fingers basically to circulate is the torsion, direction of the torsion. So that means in this direction is like this. For this side, we circulate our 4 fingers with the direction, then the thumb point to there. So this is T, in balance. And I found, at least for myself, I found this symbol basically resolve most of my issues. And sometimes when drawing is not so perfect, then we apply this direction. Sometimes it's really cause some confusions. Okay, the 2 symbols just basic to you, depends on which one you like. Okay. So now I want to derive the fundamental equations, and based upon the Again, based upon the observation of the deformations. So from this point, I'd like to turn off the slide and try to work on to the generic formulas for the chapter 3. So this is our model to use. And let me redraw the model here. And let me draw in the different orientations. Okay, so this is the length of the shaft. And the shaft have a radius c, constant. And now I'm going to do some observations. And mechanics of material is approached based upon the observation of the geometry. Compared to the other branch of the solid mechanics, we call the elasticity. Elasticity totally based upon the constitutive equation, which means that is the governing equations of the deformation. And in mathematics, those are differential equations. And two ways to approach the same problems. And most of the time, the mechanics of material approach, like we are doing now, is much easier. And that is more intuitive. But it's risky if we ignore or we skip or miss some terms, then the result will be a little bit different from the theoretical result. Okay, so, but this is the beginning, so we try this. If you could imagine, this is the 3D shaft. If you could imagine before the torsion applied, say if we mark a line on the surface, this is a marker we draw it to represent a fiber on the surface of the shaft. Okay, and that is before torque applied, so that is before deformation. So once now I want to apply the torque in this demonstration applied is in this way. So that means in this direction I apply in this. Okay. So assuming this side is fixed against the wall, or we take into this, either way, they are equivalent. Can you see that the fibers be deformed? Okay, or otherwise I try to do this way. So for example, the fiber, this one represents in this horizontal line. Once we apply the certain torque, you can see this fiber basically is tilted up at one end relative to this one. Right, so let me draw that one. So the red one represent is the deformed of the fiber. So here that is due to this portion. Okay, why I draw the torsion in this way? Because you can see I want to make the fiber deform in this orientation, my torsion must be in that way, right? So in this way. Can you see it? Okay, this is a relative displacement of the fiber. Basically, I fixed the point here for measurement. Okay, I take out the Rigidbody Translations. So now that is the first one we can observe. The second one is this. If we want to quantify the deformation of the shaft under torsions, and there's so many ways we can try. The first one is we can quantify the angle here. The larger the angle between the before and after the fibers, then that indicates that will be the index to the deformation, or index to the larger, to the magnitude of the torsion. On the other side, if you look at the side view here, if I twist it, you can see this one angle has a little bit angle of the twist, right? So basically on one side, let me draw this one here. So if this is a center, we might also use this angle, we call the angle of the twist. And here we use B. to quantify the level, the status of the torsions. And it is a very common practice. The people like to use the angle of the twist for these quantifications. It's not the unique way, but that's the common way that people adopt it. So in these chapters, we simply focus on this amount and use this amount to relate to the magnitude of the torsion applied. That'll be good? The larger the torsion, the larger the phi, the angle will be. And the relation should be linear, because here in this class we talk about is everything is elastic or linear phenomena. And the remaining is, right now we have determined the index to quantify the magnitude. So now we want to get more information, how to correlate the information to here. From here you can see, if let me get one more labels, let me call this is gamma. Okay, so from here you can see basically gamma can be related to phi through this arc length by something. If you look at on one side, gamma tangent gamma times L, this is equal to this arc length of the blue one. On the other side, this arc length, if we relate it to the phi to the radius, basically that is c times phi. That be right? So but right now we kind of step by step. So for many times, here we talk about is elasticity, and I can tell you can see I twist it very hard, but you can see that tilting angle is small. And this model is very soft. And if I would twist the shaft, for example, the shaft under the truck, and that is made of the steel or carbon steel, those one you can tell that angle should be very small in practice. So that means in practice, this is so small, so that one can be approximated by simply L times gamma, because for small gamma, that can be approximated for gamma for small gamma. Right? We simply take these approximations. These approximations can be very accurate for most of the solid mechanics model because of the Young's modulus is so big. Okay. So from here we can relate, at least phi can be related to, in terms of the gamma, is CL times gamma. And I haven't boxed anything yet, so far all the information is not that important in terms of the formula, useful formula for our exercise. But I try to do this, you can see at least phi can be related to gamma, and gamma is the tilting angle here. But think one more step ahead. What really is gamma? Here you can see I have the small cube, okay? And once we tilt it, can you see what happened to the small cube? Basically, let me label it here. So this is a cube originally attached to the fibers. If that fiber has been deformed to like this, okay, and here I want to make the first assumption. The first assumption is this: once this cube this side basically is falling on to one normal cut. Okay, so basically this side is part of the cross section. Okay, I want to make the very first assumption is this: due to the small deformations, all the particles on one cross section will move to the same on the same cross section. So that means, so that how to say that one? Let me finish this drawing first. So assuming all the particles will be moved onto the same cross section, won't get out of the plane, so the deformed shape will become like this.
Is it like the shearing stress that we went over the other day?
Yes. Yes. This is our gamma. So basically, can you tell the gamma actually is a shear strength? Am I right?
Yeah, because it's the same.
The same definition of our shear strength, right? So basically, here you can see the gamma. So gamma is a shear strength, and we use the angle of the twist to quantify. So actually, the angle of the twist is one indirect measurement to the shear strength, and through this relation. So now we figure out the shear strength. So we know Hooke's law, right? Hooke's law, that means tau equal to yes, tau equal to G times shear strength. So what is tau? So tau is here. Right? Are we okay? I'm kind of thinking sometimes to share with you, I take a break, or I just give you a few jokes. Give my brain a little fresh moment. Just take a break. When you do the presentations in the futures and try to face your front side to the audience, and if you want to turn this side to write something, try to write as quick as possible, and don't show your butt to expose your butt size too long to the audience. That is when when I was a postdoc. Postdoc, that means after I got my PhD degrees and I work on the additional researchers, basically the training, and then in the big lab, and there's American students, Wisconsin Madison, University of Wisconsin Madison, and the boys, most of the boys came from the Midwest, and to me, they pretty much the style of Tom, the role of the boy in Mark Twain's novel, The Friction.
Oh. Tom Sawyer.
Yes.
Tom Sawyer.
Almost the same style of the boy. And we have weekly presentations to our customers outside our lab. So one boy just being presented and then turn over for I think a few minutes and then begin to whine his butt. And once he finished this kind of playing, then turn around. Just give you a lesson. Don't show this kind of things in front of audience. So we're laughing, and then I learned that is very still fresh memories in my mind. So the second one I give to you is this. In terms of the experience as instructors, I know sometimes we need to prepare, but too well prepared too much. Sometimes I, at least myself, will have tendency to lose the details, which means I lose the big picture. So many times I told myself, okay, that's it. Before I came to class, okay, that's it. I don't want to look at it anymore. I just come and then, okay. But sometimes I screw up, right? Because I lose my details. The good way is I can take my lecture notes and just copy my lecture notes line by line, but that is not a good way. So I'm still looking for the compromise in between. Okay, now back to here. So, so here is a so very logic thinking, right? I skip my lecture notes. I put